All right, so it's my honor to introduce our speaker for today, Björn Hartmann from UC Berkeley. He's an associate professor of electrical engineering and computer science. Actually, one of the few people I know who really embodies the joint ECS program, as he's part of the Berkeley Institute of Design. He's the faculty director of the Jacobs Institute. He's a real maker and helps students learn how to become makers. I know him because during the Innovative Escape Expedition program, which funded largely a PL effort in synthesis, which included Björn as an HCI faculty member, I was hired as a postdoc in his lab to do some of the work as part of that expedition grant from the NSF. So, without further ado, I'd like to throw it over to Björn.
So thanks. Let me share my screen and then tell me when everything looks good on your end. So I'm going to share that. We're going to start presenting. And now turn on
Captions.
Captions. How is that? Are captions working?
That looks amazing. Thank you.
Okay, well then let's go. So thanks everyone for spending this morning or whatever time it is in your time zone with me. And I want to tell you a little bit about my path to work at the intersection of HCI and PL. So I started out actually kind of in a different corner. I was an undergraduate student in digital media design, which was a program that combined computer science, fine arts, and social sciences, and communication at the University of Pennsylvania. And that program was really geared around computer graphics, games, and then there was nothing equivalent at the master's level, so I did a straight up master's in computer and information science. My first research exposure, because of the nature of that program, was in computer graphics and animation. So think going to SIGGRAPH. But I just, this morning flipped back and I was like, what was that first paper that I worked on? Turns out I designed a declarative language for describing the animation of human gestures, but I did it without any PL background whatsoever. So if you want to be amused, you can look at that old paper. And then I kind of took a left turn, and after my master's, I had a stint as a record label owner and as a professional touring DJ, and that really started my interest in human-computer interaction. But there was some programming mixed in there as well. So let me just show you some representative pictures from that time. So on the left-hand side, this is my label partner, Jay, a photo that I took when we were touring in Japan. And what was interesting about that picture was that we started touring at that point, it was probably 2003, with a system called Final Scratch, which, so DJs traditionally have been using vinyl records. Vinyl records weigh a ton, not so easy to travel with. And so what the system did is it got rid of the standard records and replaced them with two vinyl records that only had a time code encoded on them. And so you would connect the record players to your laptop, which would read the time code and then play back MP3 files. And so that got me really interested in, okay, software, hardware, the interface, human-computer interaction. And then on the right-hand side, at the same time, I was also producing music. And a lot of kind of electronic music producers use software like Max MSP or Pure Data. So these are data flow languages that are very appropriate for audio processing, but they also have some challenges. Some people call them write-only languages, in that you create your patch, as a program is called, and then you can never understand later again what that patch does. Anyway, so in 2004, I arrived at Stanford to start my PhD in computer science in the HCI group with Scott Klemmer. And my PhD was on authoring tools for interaction designers. So interaction designers, people who create user interfaces, how do they define interactive behavior? And defining interactive behavior is basically programming, right? It's defining the logic. When these input events happen, what kind of output should happen. My real exposure to programming languages came when I almost failed my qualifying exam. So at Stanford, you have to take a qualifying exam in, I think, 3 or 4 different subjects. I picked PL as one because it sounded interesting. Clearly didn't have enough background. And so as kind of to make up for my performance, I was asked to TA the programming languages course that John Mitchell taught. And that was really one of the best things that ever happened to me in grad school. All right. Now, I want to start out by framing what I see as kind of the classical paradigm for doing research in programming tools. And that is that there's a programmer sitting in front of a machine, entering code, either executing it on the command line, or if we get fancy, they have an IDE that then interfaces with compilers, interpreters, debuggers, etc. And that canonical setting, I think, has shaped how we think about what programming tools can be and should be for quite a while. We tend to focus on the analysis of the programmer's code, and only that code, right? Only the code that the programmer has entered. And we focus on input-output being either just messages on the command line or whatever we can plug into the infrastructure of an IDE. Now, that's not entirely true. I think yesterday, Titus told you about notebooks. So that's an emerging third class, but it kind of fits into this general paradigm. And there's nothing wrong with this paradigm at all. In fact, most of my PhD was about working in this paradigm. So in my thesis research, I developed this visual way of prototyping user interfaces that involved sensors and non-standard form factors. This is based on the state charts formalism from Harrell. And I also investigated how to give you control over experimenting with different alternatives of code. But it all kind of fit neatly into this IDE paradigm. Well, first thing I'd like to do in this talk is to get us to shift away from that paradigm a bit. So what can HCI contribute to research and programming tools? One thing I think is it can change the framing of what a tool can be. A fundamental HCI principle is to think beyond the individual. So programmers aren't hermits who live in abandoned buses in the Alaskan wilderness. Their work and learning is situated in a particular context, in a particular community, in a particular time. So I think it behooves us to actually think about what that larger context is, what that ecosystem is in which code is read, written, and executed. And so you can do that for different roles, right? We could look, for example, at software engineers. So if you center one particular software engineer, they interact with team members, right? There's very little software that gets written just by individuals. They might interact with other teams within the same organization, maybe for APIs that they use. They may interact with management. They interact with a community of other peers that are outside of the organization, but have maybe shared interests, questions, insights, and then they might also interact with users. And now if we shift from professional software engineers to students, we see a similar network, just different roles. So we might have a student programmer who's working with other students on a project team. Beyond those other students, there's a larger, there are the other students in class who are not on the same team. There's a larger community of peers, either at a school or in general online. There's teaching staff, and you can probably expand this network of stakeholders. All right, so what kind of opportunities arise if you take this broader view of who's engaged in programming? Well, there's lots of value in better tools to enable different connections. So back in 2011, I became interested in a then relatively new site that by now, I'm sure everyone on this call has used. It was Stack Overflow. And so what did Stack Overflow do? Well, it was basically a Q&A web app that connected programmers with a broader community of peers. Now, in essence, what Stack Overflow did was apply HCI principles of social computing, how to encourage and balance online participation in a setting where users generate the content, and just applied it to programming as the target domain, right? And so we did this interview study, and what came out was that these kind of designing these social incentives was very effective. So one user said, I'm very competitive, and if you give me an indication that a high number is good, I will try to get a high number. So this is the reputation score, right? I don't think it's to do with reputation so much as this is a game. And someone else said, Stack Overflow is like World of Warcraft, only more productive. So here's something that this really changed how we learn about code and debug our code at large in the world. That is not about just looking programmer uses editor, right? Takes a different perspective. Interesting thing though is kind of this model is completely domain agnostic. There's not much in Stack Overflow that is actually specific to programming. And of course, the operators of that platform realized that and generalized the whole approach into Stack Exchange. And now there are dozens and dozens of these sites that you might be interested in cooking or photography or English language usage or LaTeX, etc. There's a Stack Exchange site for that. All right, so that maybe says something about what HCI can contribute outside of PL, but let's get back to kind of the core question of this summer school. So I was asked to address the question, what can PL do for HCI in programming tools? And I would argue a key answer is that PL can provide powerful techniques to computationally guide and shape these interactions between different community members because we know they are about code. And programming languages research gives us very powerful methods to understand code, to manipulate code, and to then make other algorithmic decisions. So if we take that same Stack Overflow model, right, there's a programmer and a community, and they talk to each other, and they exchange code and text. The superpower is that instead of just running a regular web app in the middle, we can inject PL techniques that guide and shape who's talking to whom about what, in which format, and when. Okay, so in the rest of the talk, I want to take this abstract principle and make that a little bit more concrete through a number of projects that I've worked on over roughly the past decade. So I'm first going to introduce a new idea. Well, it was at least new to me at the time, that we're going to guide this interaction between different community members by showing relevant hints and fixes in an editor based on what other programmers have done in their editor. You run into a problem, we'll show you some suggestions of what other people have done when they were in a similar situation. And we had a really kind of naive implementation of this back in 2010. But it raised a key question: how might we find relevant related programs and understand the differences between your program and some other program? Okay, so that was the core idea. An interesting system, wasn't all that powerful. And then second step is Well, there's maybe a programming languages inside. We can use program synthesis to create useful abstract representations of code at a higher level. And then we can manipulate those abstract representations in new user interfaces. And part of the HCI perspective, of course, is we also always need to validate when we then build these technologies that they actually improve the programmer's experience in the way we hope. Okay, so that's the general approach, and then I'm going to show you 3 examples of kind of following that approach. First, in a very narrow domain, hints for students who are solving finite automata assignments. Then from there, we're going to move from DFAs into code, and I'm going to show you 2 techniques to help students get hints on programming assignments that they submit. One is automatic visualization, and another one is using synthesis to amplify the capabilities of an expert instructor who writes manual feedback. And then I'll close out with some reflections. All right, so here's the initial idea. System was called HelpMeOut. The setting was I was doing, because of my PhD, a lot of work with artists and designers. And I became interested in non-computer science major programming labs in art and design schools. So there, often students work in parallel through some programming exercises. That means they write similar code at the same time. And the goal is usually just getting understanding and mastery of the concepts. It's not grading them that on their efforts. Now, the larger problem is students get stuck because they're just learning how to program on compile time errors and runtime exceptions. Yet there's usually only one instructor, and one-on-one debugging is kind of time constrained. The instructor can't make it to everyone. This, of course, gets amplified with large courses that we see in MOOCs, and now all the large online courses that we'll face in the near future. Okay, so core idea was, let's automatically suggest relevant hints by finding similar fixes to a problem that other students have recently applied. So we're going to redirect this interaction between student programmer and instructor, and instead focus on try to supplant it with automatically computed interactions or computationally guided interactions between students and other students in the class. Okay. So the idea here is that we have the system HelpMeOut that sits in the middle that transparently collects code fixes from peers. And when a student then has code with a fault, that system gets queried and suggested fixes and explanations get automatically shown. Here's a screenshot of what that system looked like. We implemented this for processing, which is a popular Java-based multimedia programming environment. And so here in the background, you see a student got an error, compile time error, variable must provide either dimension expressions or an array initializer. It's like, okay, not quite sure what that means. HelpMeOut pops up and says, well, here's what one student did. They inserted, a dimension expression. Or here's another suggestion. Someone just provided some literal values to initialize that array. Okay, so how did this work kind of under the hood? So we instrument their IDE and just log source code changes over time. And then we find pairs where the source previously had either a compile time error or a runtime error, but the next time it was compiled and executed, it didn't. Then we take those 2 programs and submit them along with the plain text of the error to the database, so that later, when another student encounters an error, we can submit their source and their error to the database, and we query basically who had the same error and similar code structure. And then we show that back as suggestions. Now you can go one step further. You can not just show the suggestions, you can also put the instructor in the loop. So we can look at the database and basically just rank order what kind of errors are occurring most frequently, like in the session right now. And so that tells the instructor, if you write an explanation for that kind of error, right, that will have the maximum leverage of your time. Like the most students are likely to see your explanation there. So gives the instructor a more bird's eye view and the ability to kind of leverage their time to help more students. Okay, so here I'm just showing in number 4 at the bottom that there's this additional web interface to just collect manual explanations. All right, well, this was an interesting idea. In retrospect, it had 2 major shortcomings. The first one was a conceptual shortcoming. Namely, we showed code edits. This is in the learning sciences literature, this would be called giving a bottom-out hint. You're basically giving the solution away. Is that the right pedagogical strategy? It isn't. Better is to look at the intelligent tutoring systems literature and what they've come up with about different types of feedback and use those categories to provide more abstract feedback first. So, for example, error-specific feedback might just point out what is wrong. Solution-oriented feedback suggests strategies for addressing an error without just showing you the solution that you should copy into your code. And then the second major shortcoming was just a technical one. This was a brittle implementation that really shouldn't have been done this way. But it turned out to be an interesting enough starting point for almost a decade of research afterwards. So this is where PL really would have helped this project. How do you define similarity between code submitted as a query and existing code that exists as fixes in the database? We did a really naive thing. Basically, we lexed the program and then just replaced all identifiers with generic placeholders so that variable names wouldn't matter, and then just computed string edit distance in the neighborhood of where the error occurred. This totally ignores types, it ignores inheritance, it ignores that they are functionally equivalent ways, but that looks syntactically totally different of doing things, et cetera, et cetera, et cetera. So this was like a good enough effort to publish an HCI paper, but it was probably not good enough for any setting beyond students working on essentially exactly the same code at the same time. So why didn't we use better techniques? I think it was just a structural problem. So on this project, we had 2 HCI grad students, 1 undergrad HCI intern, and 1 HCI advisor. And so our entire incentive structure was oriented around, well, what does the HCI community value? It's the idea, the concept of that interaction, along with a working implementation that works under some constraints, but kind of the generalization that this would work and be robust more broadly was somewhere on our radar, but it wasn't high enough that we said, okay, let's devote like months of effort to it. So I think that's just the, it was just the reality at that time. Okay, however, this initial idea did in indirect ways lead to a larger research agenda, right? So there's a fundamental question given to programs: how do we find and describe the difference between them at a useful level of abstraction? And so here comes the PL insight. We'll define a domain-specific language that describes either the aspects of the program or differences between a pair of programs at a higher useful level of abstraction. And then in general, what we then do is use program synthesis to search the space of programs in that DSL to find a suitable program given, underlying code that we want to compare. And then the HCI insight is, once we have that more abstract level of representation, we can write new interactive tools that operate on that synthesized DSL code. That could be turning that DSL code into natural language hints. It could be generating an interactive visualization from it, or it could be leveraging it to scale the utility of manually authored hints, as we've seen in HelpMeOut. Okay, so that's kind of the abstract research agenda, and now I want to walk you through 3 particular examples that operationalize this in various aspects. And so to start, let's step away from a Turing-complete language where things get complex everywhere you look, and just look at a simpler problem where we have very well understood tools. So we're looking at automata, right? So deterministic finite automata, a fundamental in CS education, and they have lots of practical applications as well, from regular expressions, etc. Now, a common assignment then that you would find in a theory of computation course is create a DFA that corresponds to a given regular language description. The automata tutor system that we built computes hints and displays them when students submit incorrect attempts. So now we're not connecting students to peers, but we're connecting students and instructors, because instructors provide problems and correct solutions to those problems. Students attempt to solve those problems, and then we can interpose a smart system in the middle that, if their attempts are not correct, can compute and provide them hopefully pedagogically valuable hints of what to do next. Okay, so here's an example of what the automata tutor system would do. So it gives you a web-based environment to draw automata. So a problem might be construct a DFA over the alphabet AB such that A accepts the set of all strings in which BA appears exactly twice as a substring. Student says, okay, let me work on that problem. I draw my automaton, submit it, and it's incorrect. Automata tutor can then come back and say, well, this is incorrect, but here's a hint. Your solution accepts a different but related language where it's the set of all strings where BA appears at least twice instead of exactly twice. So that's a conceptual hint that the student can then think about, produce a new attempt. We can investigate that again, and then automatically generate feedback like, well, now you're pretty close, but your acceptance conditions are not quite right. So think about which states are accept states here. Student thinks about that, third attempt, and eventually gets to something correct. And hopefully in the process, is deeply thought about the relationship of the language they first wrote an automaton for, and kind of the nuances of the problem. Okay, so how do we generate this feedback? Well, I said the main PL insight was have a suitable DSL, right? So in this case, my collaborators created Mosel, which is a DSL that can provide a declarative description of a regular language at the level of abstraction that is really close to how these problems are usually stated, right? So for example, some Mosel formulas might be the ones you see on screen here. So index of BA, cardinal of that is 2, strings that contain the substring BA exactly twice. You have components like something can begins with something. You can do modulo. You have and or constructs. And so kind of the technical piece is showing that if you have this language, you can convert forwards and backwards between a Mosel formula and a DFA. Right? So you can go in one direction from Mosel to DFA, but more interestingly, you can, the inverse problem is usually the harder one, right? you can convert any DFA to a Mosel description using enumerative synthesis of Mosel programs. So let's consider all Mosel programs of length 1. For each one, turn it into a DFA, check for equivalence of DFAs. Did we find a match? If not, go to Mosel programs of length 2, length 3, etc. So this is kind of brute force, but it works because these Mosel descriptions are usually very compact. So your formulas don't get particularly long. Okay, so then given that we now have this language, right? Well, there might be multiple possible Mosel formulas that match a student's DFA. So what we want to find is the Mosel formula for the language of the student's DFA with a minimum tree edit distance to the language of the target language, the correct solution to the program. And we once again use kind of iterative deepening to do that. And then we diff the two Mosel descriptions. And based on that diff, we can just do pattern matching and turn that into a natural language. So here we see the two Mosel formulas are essentially the same, except we have equals and greater than or equal to. That's the point of difference. So we can turn that into the natural language. Your solution accepts the set of strings in which BA appears at least twice, because that's the salient point of difference. There are other hint strategies that we implemented as well. You can look at the 2015 Tokai paper for details on that. Okay, so then the next step is, well, does providing this feedback actually help students? So here, what we then did is we designed a controlled experiment where we deployed these hint strategies in 2 theory of computation courses with 370 students across 2 universities, and then gave them homework assignments where we split the students into different groups, and they either saw binary feedback, just correct, incorrect, or they saw our hints or counterexamples. And what we found was that if you just give them binary feedback, students were significantly slower to complete problems, and students also had a significant preference for conceptual hints and counterexamples. Now, which one of these strategies then actually works better seems to be problem specific, and that's kind of still an open question. Like, given one of these problems, do you know if providing a conceptual hint or a counterexample would be better for the student making conceptual progress? That's still unclear. Okay, just a note on impact beyond this paper. Automata Tutor was then put on the web, and by now has been used by thousands of students in many different countries. And Loris D'Antoni, who back then was a PhD student, is now a professor at Madison, has greatly expanded the scope of problems that can be handled by Automata Tutor to regular expressions, context-free grammars, push-down automata, etc. So there's a archive preprint, and you can also just go to automatatutor.com to check that out. Okay, so DFAs are nice, but it seems like a restricted playground. How might we generate hints for quote unquote real code? So this the next step in our research agenda was thinking about how to generate hints and fixes for introductory programming assignments. And here we partnered with CS61A, that's the introductory programming course at UC Berkeley. And that at that time was taken by 1,500 students a semester. I think now it's over 2,000 students a semester. While that is a challenge for instructors, it's kind of great for any data-driven approach, right? You can get lots and lots of student data to operate on. So a typical assignment in that course is implement a Python function according to some spec, submit it to an autograder, and the autograder then checks it against a black box test suite of test cases not revealed to the students and says yes or no, correct, incorrect. Okay, so now research idea here is, as in HelpMeOut, log pairs of submissions to the autograder. So now we don't need to instrument the editor, because the students are already submitting that code to the autograder. And now find the pairs that go from incorrect to correct, right? Treat those as input-output examples, and then find some higher level representation of the syntactic code changes that took that program from an incorrect state to a correct state. Okay, so we collect these potential fixes that students have applied that were all successful for some program. And then when a new student comes along and has an incorrect attempt, we try to apply those fixes and see if any of those fixes makes their code pass the test suite. If any transformation successfully fixes an incorrect attempt, then we generate a hint based on that transformation. We don't give the code away, but we generate a hint based on that transformation. Okay, now what is that higher level representation that we're computing? So this is a system called HelpMeOut that we published at HCI, which basically once again introduces a domain-specific language for describing program transformations, but in a way that's much more flexible than what HelpMeOut did. Right? So here, let's take a look at these two examples. Right? We have two students working on the same programming assignment, compute the product of term 1 times term of 2 times, etc., term of n. And they have different syntax, different structure, right? One is recursive, one is a loop, but same fix in that they replace a variable with calling the function term on that variable. And so what we want to do from these edits is extract a rewrite rule kind of the abstract syntax tree of the program that says, if you see expression times name, replace that with expression times term of name. And so that's the kind of rule we would learn. And once again, the higher level principle here is, given two source program, treat them as an IO example in a programming by example system, and then synthesize in that code transformation DSL a description of the AST transformation that took the program from its first form into its second form. Now, to synthesize, to implement that DSL and take care of the synthesis, we didn't actually have to do that from scratch. Instead, we used Microsoft's Prose toolkit that Titus was involved in, and that you might have heard about it at other points in the summer school. That basically gave us the substrate that made it fairly easy to define this DSL and implement it. Okay, so let's say we have this DSL in hand. Can transformation learned from student code edits be used to fix incorrect code from other students? So the first thing we did is we ran a post hoc study where we took a semester's worth of data on a particular problem, and then basically had HelpMeOut incrementally learn these transformations, and then see if we could at any point ever help a student, because we would have a fix that would fix their submission at a certain point in their history of submissions. So here, if you look at that black circle, student number 16, when they went through the course, they had 64 submissions until they solved the problem. So they were incorrect 63 times, right? This kind of sounds like debugging something into existence. HelpMeOut, based on seeing other student submissions, found a transformation that would have fixed that student's code at submission number 24, right? 42 submissions earlier. So we could have we could have just fixed their program, but we could have also at that point shown a conceptual hint that would have helped them. Okay, so this post hoc study convinced us there was value to it, but the question still is, how do you now generate the hints? And so I'll briefly touch on two projects that took two different approaches for generating the hints. One was generate the hint automatically. And so we introduced a new technique called trace diff or trace divergence visualization, where you take the student's incorrect submission, using our whole synthesis approach, right? We find the fix that turns that program into the closest correct program. And then we execute both of them and record an execution trace for both of them. And then we can construct a visualization that says, well, at the first step, your program and the correct program that we're not revealing to you had the same state. Second step, they still had the same state. Oh, but down here, the value of the total variable diverged, right? You computed 2. In the correct solution, it should have been 1. So that's a hint that doesn't give away what the solution is, but get the student to think in the right direction. Right? So then there's some details. You don't want to show the whole trace. You want to kind of collapse it. But this is what one of those visualizations would look like. Right? There might be recursive calls. So you say, okay, 1, 2, 3, 4, like 7 calls in. Everything looks good, but you've probably gotten through your base case in your recursion, and bam, you compute an incorrect value. That's where you should start looking. So that's the kind of hint that we can now calculate automatically. We ran a lab study between showing students these hints and showing students Python tutor, which is kind of the status quo of state visualization for a program that's used in that class. So we asked 17 participants to identify and fix bugs in sample programs, and participants, this is kind of nice result, but which often happens in studies of program activity, where participants significantly prefer trace diff for its usefulness overall and to identify, understand, and fix the bug. But when we actually look at their performance, that performance is better in our sample, but not statistically significant. Like, we can't yet generalize that we would expect in general that would be true. And sometimes you end up in these situations and you say, well, okay, so what should we have done? Maybe run a bigger study. That could have just fixed it. Or maybe there's actually, you need to go back to the design and improve the design so that the benefits become clear. All right. So that was one approach. The second approach that we then investigated, and this is a project that Elena co-led, was we go back to that original idea and HelpMeOut. Let's let experts write the hints. Let's not pretend that synthesizing something and automatically visualizing operates at the same level of insight as a trained instructor who has looked at thousands of mistakes that students have made over the years. And you can just say, yeah, here's the conceptual hint I would give. Right? So we take the same infrastructure, we mine student bug fixes, we learn these code transformations, but then instead of automatically generating hints, we use the code transformations to cluster the mistakes and say, these 50 student submissions can all be fixed by the same code transformation. They might be, or hopefully are, conceptually related. And if you just write one feedback, detailed piece of feedback for the whole cluster, we can distribute that back to all 50 students who had that one conceptual mistake. And there might be 30 students over here who had this different mistake that's also fixed by a common, source transformation. Write a different piece of feedback for them, and we'll distribute it back to them. And so we built a user interface around that would show these clusters to instructors, let them also scroll through the individual student submissions to actually verify that they all share some common misunderstanding, and then write plain text feedback that you can either distribute back to the students, or you can just keep it in your database. And so next time anyone ever has a similar mistake, you can automatically show them that feedback. All right. So for this system, we evaluated that with 17 members of the teaching staff of that course. Seems like, where did you get 17 teachers from? Not that hard in a class that runs at 50 TAs per semester. So we used HelpMeOut to synthesize the code transformations from past submissions to an autograder, and then showed the instructors that clustering interface and said, here, does this work? Is this useful? Is this conceptually meaningful? And what we found is, maybe not surprisingly, the instructor said, well, I can make sense of this. I now know what feedback to write, but please don't show these synthesized fixes directly to students, right? Because some of these might just be hot fixes that that are not elegant, that produce dead code. That's just not good practice. But you can show them to me, and I can write something useful based on that. Now, we also found out that this whole system kind of relies on coverage of the autograder test suite, right? In the DFA realm, we can just test for equivalence. There's no ambiguity. But here, the correctness of the program is only so far as that the program passes a bunch of test cases. And so if that suite is buggy or incomplete, then kind of tools that you build on top of the test suite also won't work that well. All right, so that takes me kind of to the end of going around the circle of 7 years of research. So we started out in 2010 with HelpMeOut. Good idea, but we lacked sufficiently powerful techniques to fully realize it. Then building the right tools required learning this whole new language of program synthesis, building the right collaborations to then actually build systems on top of it. And that actually ended up taking 5 years, not because it took 5 years of work, but it took 5 years of all the pieces falling into place. We got really lucky with funding, and we got really lucky with having pros, so we didn't have to build the whole synthesis engine from scratch. Another thing we learned here, evaluating the impact of hint and feedback systems is very nuanced and hard. If you can run it at scale in a giant class, right, and you have n equals 1,000, but you lose insight into the individual student's experience, you can really understand that experience in detail in the lab, but then oftentimes you don't have large enough numbers to find significant results. Okay, kind of irony here at the end, HelpMeOut will probably remain the most widely cited paper just because it was there first, even though the later papers probably have more insight. And so a lesson there is, don't get too attached to your citation numbers. They do not have a deeper meaning other than something was there at the right time and got other people to think about a problem. Like, it doesn't mean that the most highly cited paper has the best solution to something. Now, I will say, though, something that is true is that papers that open a research space, in that they pose more questions for others to follow, are often more useful to the research community as a whole than papers that close a space by just providing the best possible solution that everyone will then just adopt. That might be great for industry, but it's kind of different story in research. Side effect from this whole story was also that synthesizing these source transformations in HelpMeOut turned out to be useful in all kinds of other domains, in refactoring, in helping automate repetitive edits across a code base, and follow-on work by Gustavo on that has actually just been folded into Visual Studio. So there's, now a feature in something that millions of people use on a daily basis that had its origin in a research paper some years prior. Okay, so I want to acknowledge here as I start to wrap up the project leads for all of the projects I showed you here. So Andrew, Elena, Gustavo, Loris, Rio, and Rutsmam, who really did all of the hard work and allow me to then talk about it in sweeping generalizations. And beyond the project leads, there were also many other students and advisors involved in this whole research agenda. Okay, so let me just close out with a couple minutes of reflection. So how did these projects happen? HelpMeOut was an internal project in the HCI group. It was really fast. We did it over, a summer. Everyone worked together really seamlessly because we all had the same kind of worldview. But there were real limitations of our strategy here. All the other projects were made possible by the National Science Foundation, in particular by their Escape expedition. So this is the 5-year grant that is about the largest funding category the NSF had, and it brings dozens of researchers and students together, and usually have really interdisciplinary teams and many institutions involved. Now, those large distributed projects can feel really complex, right? There's ambiguity. There's like, I don't even understand your language, even though we're both computer scientists. It's harder to grasp what's even going on. Are we headed in a coherent direction? It's slow to coordinate across time zones and different semesters. It's riskier than doing projects just in your group. And it's very real that a whole bunch of these efforts just don't succeed. They just fall flat. But when they do succeed, there's unique, impactful work that you wouldn't just do in a single research group. Okay. So another reflection, should you become an expert in both HCI and programming languages? I would say splitting expertise down the middle is really, really hard. And my primary piece of career advice is, if you're interested in an academic career, as a PhD student or as an assistant professor, pick one primary target community where you have your center of gravity that will consistently understand and value your work. So for me, that's WIST, User Interface Software and Technology. Been going to that conference for I don't know how many years, every year, submit every year, and in that conversation, know what's happening. Now, the reason for that is pretty prosaic. You'll need letters from a community at key stages of your career. And if it's a real benefit of all those letters are consistent, and not you get 3 different letters that talk about 3 totally different aspects of your work that seem to not connect in the reader's mind. Now, that being said, you want to have one focus, but you do want to learn about a second or third or fourth area. And the depth to which you want to learn about that, that can range up and down, right? You can become a collaborator in a sense that, yeah, I now know how to implement a DSL as well, or I know how to design and run a study, or at least you have the conceptual machinery and the language to talk to the expert who's going to do that piece in collaboration with you. And so then just say yes to opportunities for that collaboration, knowing that sometimes you'll lead, sometimes you'll follow, sometimes you have more effort, sometimes less, and sometimes it won't work out, but sometimes it will. Now, I see 2 common models for multidisciplinary projects. One is where you are the single lead student, but you pull in advisors from different disciplines. And then you have to sort it all out in your own head. And a second model is there are multiple students involved. Each of those students has a particular strength, and they have their advisors in that area, and they work directly together on the project. So I'm not going to go into what all these projects are, but I just want to point out I have plenty of examples of both in the last decade of research I've done at Berkeley. So there's multidisciplinarity through multiple advisors where I've worked with PL students and have been the HCI advisor to bring them up to speed on how to think about designing the interface, designing study protocols. Or also one of my students pulled in an expert in digital signal processing and music because that's what the project required. But I also have other examples where the students pair up and we have students with different strengths. So it might be HCI plus computer vision. We have a recent example there. Or it might be some of my projects combine EE students and CS students. And I've also had an MD PhD working with a CS student. So both of these models seem to work well in my mind. Okay, now I just have two more higher level reflections and then I'll stop. This is kind of universal advice that I've gotten from members of my dissertation committee when I was a graduate student, so I'd like to pass that on. So the first is from Terry Winograd, who was part of my dissertation committee, part of my whole grad school career. And he says, here was his advice on giving a good CS talk. And I think that means by extension, a good CS research project. Right? First, state the motivation. Convince the audience that the problem you're tackling is worthwhile and that you understand its structure. And that understanding may actually require doing some small study in the beginning. Then sketch a straightforward way and said, if I told you about this problem, you probably thought about, oh, I would do it in the following way. So sketch an Eve implementation and then show that it doesn't work. Show that just by thinking about it for 5 minutes, you cannot solve this problem. Then introduce the clever algorithm, show how a particular technical insight allows you to overcome the limitations of the naive approach. Right? And this is where kind of PL can really make a difference. Then build a real system around that clever algorithm, and then close the loop and show that you actually achieved some of the goals you set out in the motivation. That to me is kind of the hallmark of strong technical HCI work that takes place in computer science. Note that other disciplines may have different recipes. So HCI is very interdisciplinary. And if HCI happens outside of computer science, step 3 may not be required, right? You're still making a dent in the world if you just do good user-centered design and show that a straightforward implementation actually solves the user's problem. You've still contributed something of value. And also note, as Amy Coe said 2 days ago, bringing in HCI at step 5 is not that useful. It's too late, right? The collaboration needs to happen starting at step 1. Okay. Now, the very last piece of advice is on problem finding versus problem solving. I think in a lot of areas of computer science, for whatever reasons, we get taught an engineering mindset. Take the problem as given, find a better solution than what people have done before, right? Improve performance by X%. I'd like you to take on a design mindset where you ask, well, do we actually understand what the problem is in the first place? What can we do to find a better definition of the problem that would lead us to a better solution, maybe a totally different solution? So as PL and HCI researchers, convince yourself that you found a good problem first. Don't come up with a technique and search for applications later, right? Really be convinced that you have a good problem that is worth your time and effort. And the quote to me that sums all of that up comes from Stu Card, pioneer of human-computer interaction, who I also had the benefit of having on my dissertation committee. He said, be careful to invent a world that you actually want to live in. And with that, I thank you for your attention and turn it back to Elena.
Thank you so much. All these high-level insights, in addition to the work that you laid out, is fantastic. I wish I had gotten this as a student, but it's still helpful to hear as an advisor of young students. We are now going to follow the ICER Q&A format again. So I am going to invite all our audience members to randomly chosen breakout rooms of 5 to 6 participants. And we will reconvene in approximately, say, 10 minutes, no more than 10 minutes, to hear your refined questions from those discussions. We have a healthy queue of questions. So remember, state your curated question that you perhaps wrote down, briefly, so that we are to be sure to ask all our questions of Bjorn. So I'll start with Caroline Berger. Go ahead, Caroline.
Hello. Our question was, how do you get to the point where you can communicate with another researcher outside of your domain so you guys can both understand each other?
Yeah, excellent, excellent question. So when you first listen to a research talk in a different specialization, it can seem like a foreign language. It's definitely true. So my wife's a geologist, and if I read the abstract of a geology paper, I just have no idea what's even going on. It's like, what are these words? What do they mean? Within computer science, there's like more of a common base, but still different communities have, different things they value, different ways they use language. And I think while you are still a grad student, the ideal thing to do is, if there's another discipline you're interested in, take the introductory grad course to that subject, right? So for example, at Berkeley, we teach a course, CS260B, Introduction to HCI Research, which is aimed at all PhD students. Yes, the HCI students take it, but it's a welcome to the wide world of HCI research. Here's what this landscape looks like, and here's what contributions are. And then you get, you do a project in that realm, but it's more it doesn't necessarily have to make a contribution to the field immediately. It's really getting you familiar with that. So that is a great start. If that is not available, I like to go to, like department colloquia or other talk series where people from different disciplines come through. And it might take me a while. Like, I might not feel like I have an intelligent question after the first talk, but 6 talks in, like, okay, I'm starting to get the hang of it, and can ask a question that maybe says, hey, can you explain that to someone from outside your domain? So find those ways to engage before you jump into a joint research project.
Wonderful. Next up, Jeffrey Litt.
So hopefully the educational context can serve as this petri dish for broader contexts where you don't necessarily have 200 novices writing the exact same program. I'm curious, have you found anything surprising in terms of how well or not well studying the educational context does generalize to other contexts?
Yeah, great question. So there's always the danger that when you say, well, these assignments are, write 1 or 2 functions, does that bear any resemblance to what a professional software engineer working on an operating system faces? Now, the interesting experience was in Hefazay, the same infrastructure supported both learners and professional users, just in different tasks. right? Where for learners, like finding these code transformations was useful to generate hints, whereas for professionals, it's useful in automating their and speeding up their work. So you need to apply the same, change across 200 source files, but it isn't quite a clean refactoring. Well, here's a tool that can find all of these instances and help you with that. So yeah, it's not clear that it's not automatic that what you find in the student context transfers into the professional context, but it's also not the case that by default they're totally separate and what you do in one has no value to the other.
Awesome. Chris Martins, why don't you go ahead?
Sure. No, sorry. All right, so I actually have a related question in terms of asking kind of about the, studying some of these ideas in the educational context, which is, to what extent are so I guess it's kind of personally speaking for you, what were you motivated by educational concerns as your bottom line? And, if not, or were you kind of thinking of the educational context as a convenient test bed in a university setting to approach these things? And more generally, kind of what do you do if, maybe education isn't your bottom line? How do you navigate kind of that space of funding and publication for
Yep.
other?
Okay, yeah. So for me, so going back to what I did to my PhD, working with artists and designers who write code but are not professional software engineers. I was just motivated by taking them seriously as a group of target users and building tools for them. So that's kind of what started the HelpMeOut project. There was this kind of technical idea, but it was right from the beginning tied to the, well, here is a user group I care about, and what I want the tools to benefit them. So later on, then we switched to our introductory programming class, and that was also kind of driven by both a need and an opportunity at the same time, where our on-campus classes were getting so large that traditional models of teaching just don't work at 1,000 or 2,000 students. And so there's been, for years, this kind of need to build tools for that setting where all of the regular ways we do things don't quite work. Like, for example, at UC Berkeley, there's no lecture hall that can hold everyone who's enrolled in that class. It starts off in the performance space, like an auditorium with 2,000 seats. And then afterwards, the biggest lecture hall is 750 people. So people can't even all come to the lecture if they wanted to. And lots of other effects like that. So it really was this, oh, here's a research opportunity and a need kind of all wrapped up in the same package. Now, that doesn't mean at all that the only opportunities or the standard starting point should be within the educational space. So Elena and I and other collaborators also worked on other projects that target professional software engineers and the way they learn about APIs. And there are different ways of doing that kind of work, right? You can do it with the open source community, or you can do it in collaboration with an industrial research lab, which then might give you access to the developers in that organization. So yeah, just different models. It's just for me, education kind of felt close to my motivation anyways, and that's why I picked those particular projects.
Wonderful. Yeah. Now, actually, I've just gotten several messages from folks who are requesting for you to stop sharing your screen so they can see your face better.
Okay. We'll do that gladly. Yeah, I just had the slide deck up in case there was a question about a particular slide, but I can bring that back up if that becomes relevant.
I also want to point out that you did put a link to the slide deck in the chat if anybody missed that.
Yep.
Okay, Josh Filstrup.
Hi, thank you for a wonderful talk. One thing you brought up was kind of the PROS framework that enabled you to kind of get things off the ground more quickly. And I wondered if you could just speak to the importance of these kind of shared frameworks, both in their ability to accelerate research, but also in their ability to help us produce higher quality results, which might gain us a broader audience to get more kind of data on our research.
Yeah, thanks for that question. So I think PROS was hugely influential and enormously beneficial. So let me get at an answer in a roundabout way. So what's often quite dangerous is to make your research progress dependent on another research project that is happening simultaneously. I've written enough research code to tell you it is very, and back in the web 1.0 days, I wrote production code. The two don't have that much in common other than they use some shared languages. And so I think it's often difficult in academia to produce tools that are robust enough that other people can build on them. It's not impossible, but it requires a lot of extra effort and usually extra resources. Like you probably need professional software developers in your research group so they can do maintenance on the code, etc., after a research question has been answered and the researcher is on to a new question. And so turns out industrial research labs, because they're in an organization that is really focused on building production code, just often know better how to resource an effort to produce a tool that is robust enough that lots of people can use it. Now, the open source community can do it too, right? So there are many different ways. It just turned out Microsoft saying, hey, this synthesis thing is important enough, we have enough point examples that we should just put some infrastructure below it that can accelerate other work. That's beneficial to Microsoft, and it's been beneficial to countless researchers as well. So having, especially coming at it from a multidisciplinary perspective, where I was like, I want to use synthesis towards this end, rather than I want to make a new theoretical contribution to what's possible from the algorithmic side in program synthesis, right? Especially coming from that perspective, having something so you're not starting from scratch is enormously helpful.
Absolutely. Next up, Shivan. Shivan, you?
Hi, thank you so much for your great talk. This is more of a curriculum design question, but what I was thinking about is you had written in one of your slides that you were focusing on mastery of concepts, and instead of writing code that you give feedback based on how people who have written similar code have made those mistakes, why don't you did you think of maybe just testing concepts themselves? Like I think some intelligent tutoring systems and such systems I've seen, they use basically closed questions, like given a piece of code and you're given a couple of options, then it's like either a fill in the blank or it's a buggy piece of code and tell me how are you going to fix this. So do you think that did you find an inherent advantage in just help getting people to write code and make mistakes and then trying to fix them, or do you think you can also use such type of questions?
Yeah, excellent question. both have their place. So let's see. I don't know if Nate Weinman is on this call. I think he was in maybe earlier in the week. He's a PhD student at Berkeley working with Armando Fox on Parsons problems. So those are, you don't write the code, you just get chunks of code in a jumbled order, and your job is to put them in the right order.
Oh.
And so that is different, right? That's you're not going to make any syntax mistakes, or it's purely thinking about conceptually what the code does. And so that has benefits for conceptual understanding. At the same time, in the HelpMeOut case, for example, the goal of the class that students were enrolled in was basically building interactive multimedia installations. And so in the end, every student would do an open-ended project. And so at that point, they would have to contend with the complexity of writing the code to do the thing they wanted to do for their project, right? So I think you need both. I don't think it's the right answer that students should always write code from scratch, not at all. But there is a very important place for that, so you gain that practice if the goal is for you to be writing code afterwards. If the goal is to understand computational thinking, right, to know how to decompose a problem kind of on paper, then you don't need to write the code and send it to a compiler. So
basically dependent on the use case.
Yep.
Yeah. Okay, we are at noon, and I want to be respectful of Bjorn's time. I'm wondering, Bjorn, would you have time for one more question?
Sure.
Okay, David Mood, go ahead. You've got the last one.
Hey Bjorn, yeah, thanks for a great talk. So you had one slide that was talking about splitting your expertise down the HCI PL divide, and you motivated it sort of from a practical career standpoint, like you need letters from a particular community, et cetera. And I also recognize that practically, like you were saying earlier, like they're just sort of different languages that are spoken, and so being bilingual it can be difficult. But that said, like, I think there, like, it feels like there's, there is a lot of crossover. There is like sort of this desire for greater integration and like, personally, I would really love to be able to straddle that divide as much as possible. And I'm wondering if you feel like this is just sort of, outside of like the career, sort of perspective, like whether you feel this is just this sort of quote unquote two-party systems here to stay, or if there are sort of alternatives that you could imagine where, there is more room for someone sitting firmly in the middle.
Yeah, so maybe I stated that a bit strongly on that slide. I think being bilingual, trilingual, is excellent. It's something to strive for, but there are a couple of challenges. One is every field is just deep, right? And so I think it is easier to say, I can fully follow and understand contributions in domain A, but most of my contributions will be in domain B, than to say, I make contributions in domain A and B. Like I publish at CAV and at Chi. So that's, but I don't know. I mean, I think there are also people who can do that. But you shouldn't feel like it's not wrong if that seems out of reach, right? I think just being able to say, yeah, I read the OOPSLA proceedings and here are cool ideas that I can now implement in my system, that already puts you in an incredibly unique position, because there are not a lot of people who can say, well, here's a new evaluation technique from HCI. Let me apply that to my PL tool. Or here's a new synthesis technique. Let me apply that in a system that has other goals. That is already, I think, maybe most of the people who can do that are on this call right now, or at least the next generation of the people. So it's a question of finding a balance, and I found it easier. I'm curious about all the things, but I find it easier to have weight a little more on one foot than the other foot.
Mm-hmm. Got it. Thanks.
Absolutely. Thank you, Bjorn. Let's also thank the speaker again for a great talk with great advice embedded in it.